In this video, we're going to talk about the repeatability of measurements made in the octoscope octoBox. One of the most important attributes of a testbed is that it should be able to produce repeatable results. Because if you run a test and then get good results, but then run the same test and get poor results, at the end, you're really left with more questions than answers. Repeatable measurements are a function of both the DUT and the test equipment. The DUT, of course, or the DUT, stands for the device under test. That's the device that is being tested. Now, if the results are unstable due to the fact that the DUT itself is unstable, that's at least a useful thing to know, because at least you know then that your DUT will give different results even if placed in the same conditions. But if the results are unstable because of the measurement system itself, that's really just a problem because you don't learn anything from that. So the question that we're asking is, assuming that we have a stable DUT, how stable is the octoBox system itself? To answer this question, we ran some tests. And here's the test we did. We took two 4x4 MIMO devices and put them into two separate octoBoxes, connected through a programmable attenuator. We then ran traffic from one device to the other and used that to measure the throughput. And we collected this data using various orientations of the DUT using the octoBox built-in turntable. And here's what we found. For any given attenuation, the results, as a function of angle, were really highly repeatable. Here are the results at 0 dB of attenuation on that programmable attenuator for a full rotation of our DUT. This is run number 1, and we took 10 runs of each data. Run 2, run 3, 4, 5, 6, 7, 8, 9, and 10. And when I say that the results are highly repeatable, what I mean is that if we average the standard deviation for each of these angles, we find that we get an average standard deviation of about 9.6 megabits per second on this throughput test, and an average coefficient of variation, which is the ratio of the standard deviation to the mean value, of only about 1%. And we find that the same quality of results is seen at other attenuations as well, although there are occasional statistical variations. Here's the same data taken with 20 dB of attenuation between the two boxes. We see run 1, run 2, run 3, and as we go through the runs, we can see that there's some variability at, for example, 150 degrees, some variability showing up at 0 degrees, but overall, again, the same nice, repeatable quality of measurements in the octoBox system. In this case, if we average together the standard deviations at the different angles, we find a standard deviation of about 22 megabits per second and an average coefficient of variation of about 2.6%. More importantly, when we average the results over all of the angles, the results are really striking. So in this case, we look at the data from run 1 as a function of each of the different attenuation values used. And for each attenuation value, we've averaged this result over all of the angles. So that's the results from run number 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And quantitatively, what we find is that the average standard deviation is about 4 megabits per second, with a coefficient of variation of less than 1%. And why does it make sense to average the data over the angles? Because users are really likely to experience an AP's performance from a variety of angles. And that's the performance that really matters. So what we see from this data is that the octoBox provides highly repeatable testing time after time after time, which is exactly what's required of a high-quality wireless test system.